Hello everyone, I'm Qu Liu from HKUST. I'm glad to present our demonstration paper called RIDE, which is a system for generalized region of interest discovery and exploration. This is a collaborative work with Dr. Li Binzheng and Professor Lei Chen, and all of us are from the Department of Computer Science and Engineering of the Hong Kong University of Science and Technology. So here is the outline of my presentation. I will first introduce the background and motivation of region of interest search problem, and then I will give the formal problem definition to the generalized bias region search. And then I will overview the whole architecture of our RIDE system and provide a brief demonstration of the use cases of our system. So here is the motivation. The best region search query, also known as the region of interest query, is an important and common spatial operator for many location-based services like business recommendation, traffic jam monitoring, and wildlife habitat discovery. So here is a simple example of the ROI query. A person may want to ask to find a rectangular region covering as many as pizza shops. From this example, we can summarize two core elements of a ROI query. The first one is the query geometry, and here is the rectangular region, and the second one is the region goodness measurement, and here is the number of pizza shops covered by the geometry. The ROI query can be regarded as a generalization of the maximum range sum query, which try to place a rectangular region of given size to maximize the total sum of covered weights. The previous researches and systems usually adopt a fixed size rectangle as query geometry, which is not flexible enough in real-world spatial analytics. In our RIDE system, three types of geometries are supported: the fixed size rectangle, fixed radius circle, and radius bounded circle, which satisfy most application scenarios for the region search problem. The definitions and corresponding descriptions of the supported geometries are listed in the table and illustrated in the figures on the right-hand side. From the above definition, a query geometry is non-determined since it only contains information to define its shape and size information. For example, the radius for a circular region. To find the optimal location to place a query geometry, we need to measure the utility of a query of a geometry, which is the concept of region score. The region is the region score is a set function defined on the power set of all spatial objects, and the region score should be monotonic and self-decomposable. The monotonic constraint guarantees that a region covering O prime is no worse than another region covering a subset of the O prime. The self-decomposable constraint enables the region score to be computed in a decomposing manner. With a well-defined region score and query geometry, the ROI query can be defined as finding the location to place a geometry G such that its region score is maximized. So here is the architecture of our RIDE system. The user interface layer provides three approaches to interact with our system: the RIDE SQL, the web interface, and the Java programming interface. For a user-issued ROI query, the query processing layer will first parse the query to get the parameters like query geometry type and region score function. The query processor contains a set of efficient algorithms answering the ROI queries with different query geometries. A cost-based optimizer also works with the query processor together to reduce the total execution time. The indexing layer manages the necessary indexes for location attributes, numeric attributes, and textual attributes associated with the spatial objects. And the indexing layer serves as the data size interface for the query processing. Finally, the storage layer is where the spatial data are physically stored, and we provide an interface to several different data storage. For example, the Postgres, MongoDB, and Spark, and all of them have a native spatial extension. In this demo, the Postgres with GC extension is adopted. And the core of RAID system is the ROI query processing. A RAID SQL, which I will demonstrate later, is first passed to our parser to retrieve key information of an ROI query, including the data table used and the filter conditions, the query geometry, and score function. As for the query execution, it contains two phases. The first one is the selection and filtering of a data table, and the second step is to invoke an appropriate ROI search algorithm. A simple cost-based optimizer is used to determine the execution order. The ROI search algorithm vary for different query geometries. So this table summarizes the algorithms we used to answer ROI queries under different scenarios. For fixed size rectangle or fixed radius circle, we modify the existing solutions to enable customized score function. As for the case of radius bounded circle, we propose a novel exact solution based on a technique called circular rotation, where the details can be found in our reference of this presentation. Here I demonstrate the usage of Java interface to issue an ROI query. The user can build a query either from a builder class or directly from the raw query string. After that, the query is then sent to the driver, which maintains the connection to the spatial data storage and takes charge of query processing. The return result is put in the result set, which contains the location of the optimal region found by the algorithm and the site of spatial objects covered by this region. The user can easily iterate them using the Java streaming interface. And one can also directly submit a raw query string to the driver. The syntax is basically similar to the SQL. The select clause is modified to take a query geometry with shape or size information as parameters to trigger an ROI query. And for the region score, the maximize clause is created to take a LEGO aggregate function as input, and we also implement the several utility function to let the user to implement his own score function easily. So here is the visualization of the above query result. The markers refers to the businesses in Yelp datasite, and the right ones are the manually labeled ground truth locations. The query keywords is set to Japanese restaurants, and we vary the radius parameter from 20 meters to 500 meters for the query geometry radius bounded circle. The results are shown in these four figures, and we can see a significant coverage of the ground truth locations. Okay, thank you very much, and you can further find the sketch of our algorithm and several efficiency evaluation results in the backup site. Thank you very much.